let's do one more example, somewhat lengthy example, where we treat other orders of integration. Let's let capital D be the region bounded by the planes x equals 0, y equals 0, z equals 0, and the plane x minus 1/2 y plus 1/3 z equals 1. Set up 6 iterated integrals, one for each possible order of integration. Now we've got a lot of work to do here. Now let's go through this slowly, and let's look at all 6 possible orders of integration one at a time. And what I'm going to do is I'm going to start by sketching in a bit of information about this plane here. X minus 1/2 y plus 1/3 z equals 1. Now if I extract z x minus 1/2 y plus 1/3 z equals 1, I'm going to graph a few points on this plane to see if I can get a sense of how it's oriented in space. For example, suppose that I set x and y equal to 0, then that would give me 1/3 z equals 1, which tells me that the corresponding z value would be 3. So the point 0, 0, 3 would be on this plane. If I set x and z equal to 0, that gives me negative 1/2 y equals 1. And so that tells me that y would be negative 2 in that case, and the point 0, negative 2, 0. Here's 0, 0, 3. Here's 0, negative 2, 0. These 2 points are now known to be on the plane. And finally, we have y equals z equals 0. Wonder what would happen then. In that case, we have the x-coordinate equaling 1, because both the y and z terms in the plane have vanished. So that would give me the point right here, 1, 0, 0. And the plane that we're dealing with is sort of stretching between these 3 points at a slant. Now, also bounding this region are the planes where x is equal to 0, so this plane in the back, and y equals 0, y equals 0 being this plane here in the front, and z equals 0, z equals 0 being this region in the bottom. So let's see if we can figure out some different orders of integration that we can set up and use to describe an integral over the volume D. So let's start with the easy ones, which are the ones that we have already discussed, dz dx dy and dz dy dx, these ones where z comes first. Now looking at this region, which looks a little bit like a doorstop, like a wedge, or maybe a slice of pie that's been turned on its side, the plane acts as the top surface because it has the largest z value. Whereas the bottom surface is given by this z equals 0 down here, located on the floor, located on the xy plane. Okay, so that means that our inner limits of integration will go from 0 on the bottom to the plane on the top. So let's rewrite this plane so that I get a statement about z, 1/3 z, equals 1 minus x plus 1/2 y. Multiplying by 3, I get z equals 3 minus 3x plus 3/2 y. That slanted plane with this equation describes the top surface of the region. 3 minus 3x plus 3 over 2y. Okay, that is if z comes first. So now I need to figure out the other two limits with the order dx, dy. And in order to do that, I need to consider the shadow made by this region on the xy plane. So let me extract a picture of simply the x and y axes. And let me extract the image of this gray shadow here, which stretches from the point where x is 0 and y is 1, to the point where x is 0 and y is negative 2. So x is 1, y is 0, and here x is 0, y is negative 2. In our region, goes between those points. So with the order dx, dy, we need to identify the function bounding this region on the right side and the function bounding this region on the left side. So on the right side, we have the line that goes from 0, negative 2, up to 1, so we have a slope of positive 2, a y-intercept of negative 2. And if I rearrange this a bit and solve for x, I get x equals y plus 2 over 2 for the right limit. Whereas for the left limit, this is constant at x equals 0, right there on the y-axis. And this is valid for y-coordinates from negative 2 up to 0. From negative 2 up to 0, the y-coordinates, our function stretches from x equals 0 on the bottom to y plus 2 over 2 on the top. And this could be used to calculate the integral of some function f of xy over the volume D. Alright, let's get the next easy one. Let's get the next easy order of integration, the next one that has z in the front, which is dz, dy, dx. Then the next one will do dz, dy, dx. Now since z is still on the lead, we can recycle a little bit of our old work, because it will still remain true that our region is trapped between z equals 0 on the bottom and z equals 3 minus 3x plus 3y on the top. So we get to recycle our previous inner limits of integration. 0 up to the plane. 3 plus 3x minus 3x. Woo. Plus 3 halves y. dz. But in this case, we're going to change the middle and outer variables to have y first and then x. So now we're going to think about our region as being bounded not on the left and right, but on the bottom and top. So looking back at that shadow that we drew in the previous part of the problem, our region stretched from the line y equals 2x minus 2 on the bottom of the triangle up to the line y equals 0 on the top of the triangle. So that would provide my middle limits of integration. Y goes from 2x minus 2 up to 0, y. And then x can go from 0 on the left up to the maximum x coordinate of 1 on the right. that we're integrating as x goes from 0 to 1. So the next thing that we're going to need to do is we're going to need to try to find the limits of integration that correspond to x coming first, which corresponds to y coming first. We have 4 more of these left to go. So let's go ahead and get started with that. And let's try to, in the next phase, calculate what the iterated integral would become if we used the order, say, where x came first, and then y, and then z, for example. Now when z came first, we looked at our three-dimensional region, and we asked ourselves what function of x and y bounded the region on the top, and what function of x and y bounded the region on the bottom. In this case, when we have x as our first variable of integration, we're going to ask ourselves what function of y and z bounds our region and has the largest x values. What function of y and z bounds our region and has the smallest x values? Now looking at this region, the part of this door wedge which is furthest in the positive x direction is still given by this outmost facing plane here. So let's take the equation of our plane, x minus 1/2 y, plus 1/3 z minus 1, and let's rewrite it so that it's an expression with x isolated. 1 plus 1/2 y minus 1/3 z. That plane has the largest x values bounding this region, and so it's going to perform as our upper inner limit of integration. It was 1 plus 1/2 y minus 1/3 z. Now on the bottom of the region, the x values are supposed to stop at x equals 0. So let's put that in. X equals 0 is the lowermost x at all points. Alright, now moving one layer out, we have the dy dz integral. And previously, when z came first, we considered the shadow, the projection of the three-dimensional region onto the xy plane. If z came first, project onto the xy plane. In this case, because x has come first, we're going to consider the projection of the region onto the yz plane. So what I'm going to do is I'm going to put a sketch on the side, which consists of the positive y-axis and the positive z-axis. And I'm going to make a note that this point ran between the point where x and y and z, x and y were 0 and z was equal to 3, as well as the point where x was 0, y was -2, and z was 0. And our region ran between those points. So now let's think about, on the horizontal axis we have y, let's think about what function bounds our region in the horizontal directions. On the right-hand side, we have the constant value y is equal to 0, corresponding in this drawing to the z-axis. On the left-hand side, we have the line going from -2, 0 up to 0, 3. So it has a slope of 3/2. And a vertical intercept of 3. And if we write this in terms of y, we get subtract 3, z minus 3, multiply by 2/3, we get y equals 2/3 z minus 3. And this is valid for z values between 0 at the lowest and 3 at the highest. So our middle limits of integration corresponding to the middle variable y is allowed to go between 2/3 z minus 3 all the way up to y equals 0. And z is allowed to go between 0 at the lowest all the way up to z equals 3. Now, similar to that, if we want to switch the order of integration to dx, dz, dy, then we can recycle some old work because our x limits will be unchanged. They'll still go from 0 to 1 plus 1/2 y minus 1/3 z. But this time, z will come before y. And so I need to return to this region in the yz plane and think about what functions of z bound this region in the positive z direction and in the lower z direction. And we have the lines that on the bottom we have z equals 0 on the y-axis. So we'll integrate from z equals 0. And on the top we have the slanted line with the equation that we found before. So we have 3/2 y plus 3. And this is valid for coordinates of y stretching from, at the lowest, -2, the highest y coordinate 0. All right, we now have 2 more orders of integration left to go in this problem, corresponding to having y in the lead instead of either x or z. So here we have the order dy. Let's say we do z next and then x after that. All right. Now let's once again look at this plane. There's so much writing on this. Actually, the document is lagging. This is pretty funny. Let's have a look at this plane here. We have this plane. This plane, though, is stretching in the direction of the negative y-axis. Here is the negative y-axis stretching out toward y equals -2, which means that the y values of this plane, since they're back here toward the negative y-axis, the y values of this plane are negative, or in other words, smaller than y equals 0. So if we take this plane, that plane's equation, where y is isolated, is going to represent the lower limits of integration. Plane is on negative y-axis. The y values are smaller than the y equals 0 that we have. So that means that if I take the equation of the plane and isolate y, let's solve for y, 1/2 y is equal to x plus 1/3 z minus 1, 2x plus 2/3 z minus 2 equals y. Because this plane has the smaller y values, this is going to represent the lower limit of integration. Y equals 0, who has the higher values, this will represent the upper limit. So here we go, integrating dy, dz, dx. The lower y limits come from the equation of the plane, where y has been solved for, -2. And the upper limit is 0, because it has a larger y value than any point in the plane of our function. Okay, now when z came first, we took our region and we looked at its shadow on the xy plane. When x came first, we looked at the shadow on the yz plane. And now that y has come first, let's look at the shadow on the xz plane. Remembering that this region stretched to 1 in the x direction and 3 in the z direction. So let's see what line on this two-dimensional shadow has the largest z values. On the top of this region, we have the line going from 0, 3 down to 1, 0. So this line has a slope of -3, I suppose, since it's going down by 3. And it has a y-intercept, or I should say a z-intercept, of 3. On the bottom of this region, our z value is equal to 0. And so this gives me the middle limits of integration. On the bottom, z is 0. On the top, z is -3x plus 3. And finally, the x-coordinates that are valid for this region stretch from 0 at the bottom to 1 at the top. 0 to 1. And finally, the sixth and last order of integration, which is dy, dx, and z last, of our function f of x, y, z. We can steal the limits of integration for y that we used in the previous example, 2x plus 2/3 z minus 2 for the plane. Minus 2. And then let's analyze the shadow of the region on the xz plane. And let's look at the equation of this line that bounds our region in the positive x direction. We solve this equation for x. We get z minus 3 all over -3 equals x. And that's our rightmost function. On the left, we have the value x equals 0. So x stretches between 0 on the bottom and z minus 3 over -3 on the top. And the z coordinates for this region that are valid stretch between 0 on the bottom and 3 on the top. And that's it. All 6 possible orders of integration for this doorstop shaped region.